So we now talk about the path lifting property. So you have a space X and you have a space Y and you have this covering projection P onto X. Now say you have a path in X. So obviously this path will come from an interval from 0 to 1. So this is a closed and a bounded interval. So from here you apply, say, map U to it, and this will give you a path in space X. So say this part is U of 0. So this is the path, this map U, and this P is the projection. Now the path lifting property says that basically you can lift this path into space Y. So this path we are going to lift into space Y. So the new path which we get is, say, it's U of tilde, and this is such that this, say, U tilde of 0 is Y, starts at some point Y. Then if you apply the projection map to Y, it will get mapped to U of 0. So P of Y is U of 0 and U tilde of 0 is Y. So this map is starting at Y. You project it. These initial points will match with each other. So this is the initial point. This will match with this. So let us prove this result. So basically it just talks about subdividing this interval I into equal parts. So to start with, you start with the cover of X. So you have a cover of X. This U is the cover. These are the sets, and all these sets are evenly covered by projection map. So you're saying this cover is evenly covered by P. Now this is important. This we are going to use later. So this is evenly covered by P. Now you have a cover of X. So that cover of X will also cover this path. So once that cover of X covers this path, you can get a cover of interval I by taking U inverse of the cover of this path. So U inverse of this U. So U is the map. So U inverse of this curly U. So curly U. So U inverse of this curly U will give you a cover of this interval I. So I'm just taking this U inverse of this curly U. So you have a cover of interval I. Now since this is closed and bounded, that it is compact, therefore it will have a finite subcover, and we are just going to choose a Lebesgue number in this subcover. So say the Lebesgue number you get is 1 by n. Yeah, n could be anything really small. So basically what you do is, once you get this Lebesgue number, you split I into small intervals of length 1 by n. So you have 0, 1 by n, 1 by n to 2 by n, 2 by n to 3 by n. Basically I minus 1 by n, comma I by n, all the way to you have n minus 1 by n, comma 1. So now what you do is that, say ui corresponds to the ith part of the path. So this is ui, correspond to ith part of the path, and xi is, you take the precisely that ui part. So say xi is this. So if t lies in this, so if this is the part which is I minus 1 by n, comma I by n, so corresponding to this you have ui of t right here. So this is how you choose all the xi's. Now all these xi's are evenly covered by P. Now why is that? Because you start covering the space with the cover itself is evenly covered by P, and this is just part of this cover, and yeah, so these xi are evenly covered by P. Now once you say these xi are evenly covered by P, then you immediately get this map. So this is for an even cover. This D1 is a discrete set. This should be D1 right here. So you have a projection map here. You have some continuous map, say phi here. And then you have a map here. So this is also, so this map here is, say, U1 tilde. So we will get to this U1 tilde, how it comes about in a minute. So let us first focus on this map phi. So this is just a projection map to D1. So what phi does is it takes this point y in the P inverse of x1. So x1 lies somewhere right here. So this is x1. So according to the definition of even cover, we know that this phi is a homeomorphism. And we need to define this homeomorphism. So we are going to define this homeomorphism so that we get a lifting. So what we do is we take this y and we basically map it to u of 0 and d, where d is discrete. So basically we are choosing y such that the y will get mapped to u of 0, and then there is some discrete d, some discrete element d. You take a projection map, you have d here. Now this ui tilde is nothing but lifting of this path u. So we are talking about u1 tilde because this is the lifting of path starting from right here. So say this portion like this. So this portion might be, say, u1 tilde. Is it nothing but lifting of this path? So this is a continuous map, u1 tilde, because it's just a path lifting. This phi is continuous from our definition of an even cover. And then you are projecting it to just map D1. Now this is a connected space. So since 0, 1 by n is connected, the composition is a constant because you're ending up from a connected set through a series of continuous map to a discrete set. So therefore you get a constant map. So then you can define this lifting ui tilde of t. So in this case we are just focusing on u1 tilde of t is nothing but this phi inverse of u of t comma d. And here this t is between 0 and 1 by n. So basically now we have succinctly defined this path right here. So this is u1 of tilde. So this map, this is equal to phi inverse of, where phi is nothing but a continuous map of u of t comma this d, which is a constant. So this d could be any number. It could be 50 or -1. It doesn't matter. So this gives a unique continuous lifting of u1 starting at y. So you have a unique continuous lifting starting at point y. Now similarly you can construct u2 tilde for u2. So now you have, say, u of 2. Again you will say this u of 2, you have corresponding x2 here. So for u of 2, first thing is you have corresponding x2, which is nothing but this small part of the path u of 2. Now you will say this is evenly covered. Since this is evenly covered, you have the map p inverse of x2 to x2 times d2 to some d2. Then you will again have some interval from 1 by n to 2 by n, and then you will say this is getting mapped to a constant. Since this is getting mapped to a constant, you can now have a unique lifting, and this unique lifting would be u2 tilde will be equal to phi inverse of, again you will have ut comma, say, another constant, say d2 now. And the only thing you will say is that you will keep the endpoint of the first path, this is the endpoint of the first pass, is equal to beginning of the second path. So this path which ends here is u1 tilde of 1 by n So this has to be equal to the starting of the second path, which is u2 tilde 1 by n, and you just patch them together to get a u tilde starting at y.